All right, so we're going to take a deeper dive into quadratics in this video. I don't think I've shown you yet. Let me get a full screen here. I don't think I've shown you yet how I sketch a quadratic. We've done a lot of do this, get that. We've had a lot of repetitive practice, 40, 45 lesson sets. Who knows where we're at right now. But that repetitive practice is there so that the mechanics of putting a quadratic in graphing form and sketching, we've got some practice. So therefore, you've got a frame of reference now to follow the discussion we're about to have. I firmly believe that Algebra 1, Algebra 2, and pre-calculus form the foundation for the study of calculus. Okay. And you have to be strong in these areas. Got to have a good foundation in order to understand the concepts coming from the calculus course. In calculus, we basically, I think, and I could be wrong, this is just my opinion, having worked with this material for most of my adult life. Calculus is about rates to amounts and amounts to rates. That tells me that in this foundation here, we should be highlighting rates. All right, and I've started to even talk about accumulation of amounts in some of the other videos. I haven't been as consistent in my showing it in each lesson set. I said I would, but I forget to. I'm getting very forgetful in my old age, as you know. I make careless errors on almost every video, but getting a lot of practice, and a lot of practice is going to help you understand the material at a deeper level, which is what we're going to start to do in this video. So I'm hoping that I can pick out different functions and dive into them a little more deeply. So this is a single problem video. Well, single topic. Let's put it that way. I've got 4 or 5 quadratics that we'll put in graphing form and sketch and find the roots. And I'm hoping at the end, it becomes a 20-second problem. Okay, sketching and roots, 20 seconds. All right, let's see if it happens. All right, so we want to strengthen our understanding of rates. How? Well, how do we determine how something is changing at an instant? Well, we're going to use Algebra 1 concepts here. Oh, by the way, this is René Descartes. René Descartes, see, going back and forth. I found René. Somebody help me find René. I should give a reward for that. Now I'm feeling better. All right, so Algebra 1. Let's just look at x squared. I've had these tables up before. They're in a lot of different videos, but let's look at them again. And let's look at a curve and what a tangent tells us. All right, so a tangent is sharing a point on a curve, and the slope of that tangent is basically telling us at what rate things are changing at that instant. So we can use some Algebra 1 to help us figure that out. Change in y over change in x is really change in output compared to change in input, miles per hour. Think about that. If I tell you you're going 10 miles per hour, you're probably a slow jog, maybe on a bike. If I tell you you're going 100 miles an hour, you're probably speeding, and I want you to slow down. Okay, please go the speed limit. But it gives us important information very quickly. And we can get a feeling for rates of change. And here I am looking at the quadratic from a numerical standpoint. I suppose I should have put a graphical one up here too, or a geometric rate of change. But let's just look at the numerics. All right, what did the numerics tell us? I've got 3 decimal units of change from 0 to 0.001, and I've kept that standardized. All right, I've got a standard rate of change there. And I can look at the first 3 digits of change. And if I divide those 3 digits by 0.001, I'm getting a feeling for how we're changing at 1, at 0, at 2, and at 3. At 0, not changing much at all. At 1, going up at 2 to 1 by divide by 0.01. 2 to 1. At 2, 4 to 1, and at 3, 6 to 1. Well, if you think about those numbers, I think you got a little pattern. Now, what I forgot to say over here was, as we zoom in on our tangents, what used to be a curve shape, I guess I did a picture here, zoomed in, it looks linear. Now, I might be changing from 0.01 to 0.02. That's not a very big change. But if I did that on a calculator or a computer, this curve is going to look linear, which means we can talk about its slope. How are the outputs changing compared to the inputs? All right, and it seems like there's a pattern here. Does seem like there's a pattern. All right, and I'm using user-friendly numbers, counting numbers like 0, 1, 2, 3, which means we don't have to get caught up in the minutia of the calculations. We can think about the rates of change. And if we do, we can see that at 1, you square it, you get 1 unit of amount, but it's going up at 2 to 1. At 2, 4 units, 4 square area, going up at 4 to 1, so on and so forth. And it seems like we have a formula for the rate of change of the quadratic x squared. Quadratic, quad, 4, Latin, 4-sided. A square has 4 sides. Okay. I think all of algebra and algebra 1, algebra 2, pre-calculus, and calculus, I think you probably could say, what can you do with a rectangle? Lots you can do. You can do the product rule and the quotient rule with a rectangle and see it. Calculus. All right, getting off. I'm going off on another tangent. So let's get back to this. All right. So can you tell me what probably is the next? I hope so. I hope you can do that. And how about the preceding one? Hope you did that. Does it seem like it won? I might be going down at 2 to 1 here. And over here, does it look like maybe I'm going up at 2 to 1? Little symmetry. I hope so. I hope so. So I call those user-friendly numbers. All right. So let's look at another quadratic with some more terms in it. And let's look at how things are changing. Okay, from 0 to 0.001. And I'm only looking at the first 3 units of change. All right, I could, let's see if I can come back to one of these situations. Oh yeah, I'm way back here, Renee. I'm way back here. All right, give you the notion of a limit. Might as well do that. So let's say that I have 1.001, but it changes to 1.000000001. Okay, what's that product going to be when I square it? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I obviously did that without a calculator. Must be a pattern. Must be some coincidences here. And you would be right. But if I divided this by 9 decimal places, 1, 2, 3, 4, 5, 6, 7, 8, 9. I hope you see the 2 to 1 ratio hasn't changed. All right, so how does that help us? Well, we're getting there. Here are some more table values, except this is x squared minus 6x plus 3. We're going to see how it changes. Just 3 decimal place accuracy. 0.001, no change from the quadratic term, minus 0.006 plus 3. When we put a 1 in, 0.002 divided by 0.001, right? 001 gets us tenths, hundredths, 2,000ths units of change. Whereas over here, I'm going down at, I hope you can see the change here is 6 to 1. All right, it was actually 6 to 1 here too. If I divide this by 0.001, I'm going down at 6 to 1. I'm going down at 6 to 1 from this term. I got a feeling that we can call this constant change. Right? The change seems to be constant from one y value to the next. Whereas this one seems to be variable. And I think we said that that rate of change is really 2 times the x value. And this rate of change seems to be consistently -6. And if you're seeing change with the constant, KONS T-A-N-T, and that is how you spell constant. Don't give me a hard time here now. Don't be like my grandson, tells me it's a C. Hmm? If you see these numbers change, please be in touch. We talked about it in other lesson sets, but maybe you're afraid to be in touch, but don't be. Don't be. You love talking to folks who, whatever, just be in touch. Okay, so this looks like it tells us something about rates of change. Huh, interesting. Yeah, and if we draw a quadratic, let's do one with a cup shape up, and we zoom in right there. I wonder what the tangent would look like right there. Sure seems like it's flat, like things aren't changing much. Well, I wasn't going to draw the squares, but now I have to. So what is 2x? If this is x times x, well, I guess that's 2x. Geez, it seems like the length of the side of the square, if I change by 0.001, the bigger the square, the bigger the changes. No square? Pretty hard to draw the two x's when there's no area there. Don't think things are changing much. And I hope you say that the slope here is 0. I wonder when that equals 0. Sure looks like 3. Huh. I wonder if I got rid of one of the x's and one of the x's here. Sorry. Didn't mean to do that yet. Okay. Really talking about multiplication here. All right, because x squared changes by 2x. So I got ahead of myself. I'll come back to it later when we get over there. All right. At the y-intercept, let's see. Let's go over here. At the y-intercept, let's use this function right here. I know when x is 0, there's no change. And what are you looking at? I already answered my own question, so I'm not going to. But when I put into a polynomial, I don't care, ax to the n plus bx to the n minus 1, all the way to a constant. All right? When I put a 0 into a polynomial, what am I finding? What does C give me? I hope you say the y-intercept. Okay, so we can see the y-intercept is 3, but what do we now know? Well, that's not changing at 0, and this is going down at 0.001 into negative 0.012. Well, that's a heck of a coincidence that I'm going down at 12 to 1 at the y-intercept. Well, that's useful information. Oh, and I know x squared changes by what? Well, wait a minute, I don't want to change it here. Let's do the rate over here. All right, I know x squared isn't changing, right? But at x equals 1, I'm going up at 2 to 1. But if I'm doubling that, I'm really going up at 4 to 1 when x is 1. And I know that that's constant change. And if I want to find, again, I got cup shape up. If I want to find that x value, well, the slope of the tangent is 0. Sure seems like that's a 3. Now, what have we been doing to this point in time? We've been doing minus b over 2a, which is quick too. That's quick. Minus b, 12 divided by 2 times 2. Boy, what a coincidence. That's also 3. So how do I sketch? How do I sketch? What do I know? Well, one thing I know is the shape. And the other thing I know is that actually is the tangent line to this shape. So I look at that and I go, okay, I'm going up at 12 to 1. So this is that line. That's the tangent line to 0, 5. And I think I know something about the shape. Minus x squared on the right-hand side's going down. So I think I immediately know that I'm on this side for the y-intercept. 0 gets me 5. It's a given. I've got the shape. And I know that x squared, this, changes by 2x. And if I multiply it by -3 and I add 12, then that's the tangent line when I plug in 0 to this location. I think I said that pretty awkwardly, which is why I like repetition, because the next time I talk about this, I hope I do a better job. All right, so I can see minus 6x plus 12. Can I see it from here? And can I set that to 0? Sure looks to me like that's a 2. Can get it pretty quickly. And if I plug a 2 in, I know that's 24, and I know I've done so many that I can cut that in half and add 5, then that gets me 17. And now I know my roots. I measure my roots from x equals 2, because I got to go to the right and I got to go to the left in order to hit a height of 0. So how far do I have to go from 17 to 0? I got to go down 17, but if I'm multiplying by -3, I got to divide by -3, and if I put it in graphing form, I got to do a plus minus, and there we go. We got our roots. And there's a quadratic graph, and the roots in 20 seconds or less. Why don't you try? Why don't you try? Go ahead, time yourself. I'll give you 20 seconds. Do, 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 do. I'm sorry. I'm sorry. I don't have the greatest voice I know. All right, so what do I see? I see 8x minus 40. So I now know that 5 is going to be the x value of the vertex. Minus 200 becomes minus 100, plus 7, minus 93. I know it's cup shape up. And what's given? The downside gets me 7. So 0, 7, and I'm on the downside. Right? I got a negative slope on a cup shape up. Now, what have we done? We've done minus b over 2a. 40 divided by 8. Well, there's your 5. Still going to be the same way here. Now, I got to plug it in, right? But there are shortcuts if you put the effort in. If you put 5 in here, 25 times 4, 100. Minus 200. Plus 7. What did I do? I added 100 to minus 200, which cuts it in half. In the playlist, I'm sure there's got to be a video about that process. And in calculus, we call this what we were doing, dy over dx. And I think as students, you should hear this now before you get to a calculus class. Because folks are not going to draw these squares. At least I took 4 calculus classes, in order to be able to teach it here. And I took 2 in college and then 2 during a sabbatical year to get up and running. And if I change by 0.001, we know we have 9 units of change. And if I just do that x distance, what happens to be 3, I get 0.003 units of change. And if I do this one over here and call that 0.001, I know it's not drawn to scale, but I get another 0.003 units of area. And what I've really done is made the square a little bit bigger. And then I look at adding these up, and that's where we got the 9.006001. And that is the 0.000001 because I'm squaring that here. And that's the change in area at the cusp, which is negligible. All right, so try another one. Try another one. Okay, and see what you can do. 20 seconds. See if you can sketch that and find the roots. Huh, boy, that function, 40x plus 7, combined with this function, they're both pulling up on the right side. Boom. Okay, lots of nice things to think about. And what are the roots of this? Well, they're real, right? I know I'm going to go through y equals 0. Doesn't have to be 0, it could be any number, and I can solve just as quickly. Where am I measuring from? -5. Where is this x over here that gets that intersection? Looks like it's to the right of -5. Where am I over here to get that x, to get that intersection? I think I'm on the left side. Hopefully that explains that. And if I'm squaring something, some x value, and I'm solving an equation, then I need a square root. And how far do I have to go? 93 units. And if I'm multiplying by 4, then I think I better divide by 4. So strongly disagree. I don't know who wrote that, but I hope they don't. All right, no, I'm not sure whose classroom I'm in, but I'm not going to lose Rene Descartes this time. So let's put this in graphing form. In graphing form, we now have 4x plus 5. Why do we say x plus 5? Because the smallest area you can have is 0, and you wouldn't even show the shape. All right, and if we're at a minimum, then we're at a minimum squaring moment, and that happens at -5. So how do I turn that number into the side length 0? By adding 5. Hopefully that adds a little color. And I said minus, what was it? -93. So you go ahead and do the solving of that. What's the first thing you're going to do? Add 93. There it is. It's the next thing you're going to do. You're going to divide by 4. There it is. What's the next thing you're going to do? You're going to undo squaring. Well, that's that. And the fundamental theorem of algebra says whatever the highest exponent is in the polynomial, that's how many answers you're going to get to an equation. So we're getting 2 answers to this equation. And I'm measuring from +5, so I'm going to bring that over. So let's substitute that now into our equation. Let's let our x equal that. Again, I'm getting rid of some nice stuff over here. Not sure what was written, but it's gone now. So that's my answer. I'm going to add 5 to that with a square. I'm going to put that there, put a 4 in front. I'm going to subtract 93, and I'm going to see what my amount is when I plug in my answer. What's the first thing I see? That. When you square a positive or a negative, you get a positive, and you don't have to write a positive. What happens when you square a square root? I think those are inverse operations. What happens when you multiply by 4 and divide by 4? I think that disappears. Okay, so what do I do when I look at this? In my mind's eye, I take the shape. I look at the middle term, and I know I'm on the upside. So I immediately put 0, 7. That means I don't have to worry about this x. I know it's negative. So I don't have to worry about the pluses and the minuses. All I got to do is double the 4 and divide it into 40, and that's 5. And I know it's to the left is 0. So I would have done this because I almost made a mistake, right? I know I'm negative, so I do that. And then all I have to do is 40 divided by 4 is 10, cut in half is 5, and I've got that number. I plug it in here, -200. I know at the vertex I can cut it in half and add 7, and there's my -93. All right, so I think you can do all of that in 20 seconds. Takes a little practice, but when you've done tens of thousands of these, like I have, it's important to me to be able to do these in 20 seconds or less. So, your turn. Last one. 20 seconds, time yourself. Wouldn't be a tough thing, I think, to be able to try this at least. All right, so how about 20x minus 7? All right, you take 20 seconds and then I'll attack it. All right, I'm going after it. Oh, I like that number. I think I'm done. Roots. There. That's a 2, by the way. Yeah, I could have made a careless error, right? Because, yeah, I'm on the screen. This is a lot of pressure. Let's check minus b over 2a. Minus 20 divided by 4, negative 5. Oh, good. I didn't make an error there. Going up at 20 to 1 here. Let's go backwards 4 units at a time. So that's 0. At negative 1, I should be going up at, well, let's actually get the what's called the derivative, which is the dy over dx. If I'm going up at 20, I should change by 4. So I should be going up by 16, then I should 12, then 8, then 4, then 0. How many jumps did I make? 1, 2, 3, 4, 5. Oh, yeah, 5 jumps. Because I know x squared changes user-friendly, right? Slope at 0, 0, slope at 1, 2, slope at 2, 4, so on and so forth, right? So I'm going up, I'm accelerating my slopes by 2. Might as well plant a seed here. And if I double that, then from user-friendly number to user-friendly number, my slopes are changing by 4. And so how did I get to a slope of 0 from a slope of 20 to 1? How many times does 4 fit into 20? I went back 5. I mean, there's other things to see here. And that's just opening the door. Opening the door. For instance, now I'll stop there. I don't want to keep talking. Deeper levels still. Let's just say that there's more to learn. All right, but hopefully this moves the needle a little bit in terms of your ability to conceptualize, because you're going to have to when you get to calculus if you take it. Very deep conceptual study, as far as I'm concerned. I think it's got a lot to offer in terms of user-friendly Algebra 1 principles that move into that area of study. But I'm rambling now, so I'll hush up. Okay, hope that helps somebody. And then when we do lesson set 43, and it's mechanical, do this, get that. I hope there are some moments when we do more of these, when I do more of these deeper dives into some of the things we've studied this semester, that you pause a little bit and try to recall some of what being talked about here, because it's important. If you're going to understand calculus, it's important. All right. Good luck with your studies.